This video will show you how to use the infinite series e equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial and so on to prove that this number e is irrational. This proof is given by Swiss mathematician Euler in 1737, so it has a long history. The proof goes like this. Suppose E is equal to P over Q, where P and Q are integers with no common factors. Let E equal to A plus B, where A equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial all the way to 1 over Q factorial. And B is equal to 1 over Q plus 1 factorial plus 1 over Q plus 2 factorial plus 1 over Q plus 3 factorial plus the rest of the term. So A is actually the partial sum of the first Q plus 1 term, and B is the remainder. So the E is equal to A plus B. Then we multiply both sides of E equal to A plus B by Q factorial, so that E times Q factorial is equal to A times Q factorial plus B times Q factorial. Since E equal to P over Q in our assumption, so E times Q factorial is an integer since Q factorial over Q is an integer. Now observe that A times Q factorial, which is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus, and the last term of A is 1 over Q factorial. Now multiply the whole expression in the bracket by Q factorial. By using the distributive law, I have Q factorial plus 1 over 1 factorial Q factorial plus 1 over 2 factorial Q factorial plus 1 over 3 factorial Q factorial and so on until the last term, which is 1 over Q factorial times Q factorial. Now this number A times Q factorial is an integer, as Q is a number greater than or equal to 1, 2, 3, 4 and so on all the way to Q. Why is this an integer? Let's look at one of the term. Examine this term. And you'll find that Q factorial over 3 factorial is an integer because Q is number more than 3. Q factorial is 1 times 2 times 3 times 4 times 5 all the way to Q, and 3 factorial is 1 times 2 times 3. So after the cancellation, I have this an integer. Repeat this argument for each of the term. You'll know that each term will be integer. Therefore, A times Q factorial is an integer. Now, we know E times Q factorial is an integer. A times Q factorial also an integer. Therefore, B times Q factorial is a difference of two integers. Therefore, B times Q factorial is also a positive integer, since B is positive. And let's denote this conclusion by asterisk here. By examining closely, B times Q factorial is 1 over Q plus 1 factorial plus 1 over Q plus 2 factorial plus 1 over Q plus 3 factorial all the way to infinite number of terms times q factorial. And this is equal to q factorial over q plus 1 factorial, q factorial over q plus 2 factorial, q factorial over q plus 3 factorial, and so on. After cancellation, the first term is 1 over q plus 1, second term is 1 over q plus 1 times q plus 2, the third term is 1 over q plus 1 times q plus 2 times q plus 3, and so on. Now, we know q is integer, so q plus 1 will be greater than or equal to 2, q plus 2 will be greater than 2, q plus 3 will be greater than 2. So therefore, the factor q plus 1, q plus 2 will be greater than 2 times 2, which is 2 squared, q plus 1, q plus 2, q plus 3, since q plus 2 and q plus 3 is greater than 2, so therefore q plus 1, q plus 2, q plus 3 will be greater than 2 times 2 times 2, which is 2 power 3. Now, b times q factorial is equal to 1 over q plus 1 plus 1 over q plus 1 times q plus 2 plus 1 over q plus 1, q plus 2, q plus 3, and so on. And we know that q plus 1 is greater than or equal to 2, q plus 1, q plus 2 is greater than 2 times 2, which is 2 squared, q plus 1, q plus 2, q plus 3 is greater than 2 times 2 times 2, which is 2 cubed. Therefore, b times q factorial will be less than half, plus half squared, plus half cubed, plus half 4, and so on. If you recall the geometric series a plus ar plus ar squared plus ar cubed, and so on, the sum will be a over 1 minus r if absolute value r less than 1. Apply this to the infinite series, half plus 1 over half square, then you'll find that this is my a here, the r is also half, common ratio, therefore b times q factorial will be less than half over 1 minus half, which is 1. That means that b times q factorial will be less than 1. But we already know b times q factorial is greater than 0. But we also know there are no positive integer less than 1 greater than 0. So this contradict is a positive integer, and now we find that b times q factorial is between 0 and 1. That means e equal to p over q cannot be true. So e must be irrational.